Hello again. Welcome back. Okay. So, continuing our work from the Practices of Statistics 5th edition, Chapter 11, dealing with chi-squared distributions, I want to take a look at these couple of sample problems. Right. And the setup here is that we have some people that believe recycle problems are lower in quality than other products, a fact that makes recycling less practical. Right. And the data on the attitudes towards coffee filters made of recycled paper from a random sample of adults is shown. Notice that we have a single random sample. Okay, right, and from that random sample we get information on our buyers and we get information on our non-buyers. But because it is a single sample of adults, we have a chi-squared for independence. Alright, we did not sample buyers and non-buyers separately. Okay. We did not sample our buyers and our non-buyers separately, so that's going to give us a chi-squared test for independence rather than a chi-squared test for homogeneity. Okay. If we had said, hey, let's sample the buyers, find out their quality ratings, let's sample the non-buyers, find out their quality ratings, and control my groupings, then it would be homogeneity. But because it is a single random sample and we get the information, then we have chi-squared for independence. Okay, so our first step we're asked to do is to make a well-labeled bar graph that compares buyers and non-buyers' opinion about recycled filters. Looks like we're missing an S right there. Okay, and to describe what you see. So pause the video, try it out, unpause, and check your work. Not sure where to proceed? Well, a well-labeled bar graph, if we're going to talk about independence, look to see if there is an association. We could have it be side by side, or we could have it be segmented. If you look in the back of the book, they're going to show you a side by side in their answer. So our setup, I'm going to show you a segmented. So I've started to get the setup for this segmented bar graph. Okay, I have a bar graph that's going to represent my buyers, and I'm going to have a bar graph that represents my non-buyers. Okay. Now, in order to determine my segments, I need to figure out my totals for this two-way table. To get those totals, I can sum up to find out the total buyers, 36, the total non-buyers, 97. Do the same thing going across my columns based on quality rating. And when I go across those columns and get those sums, right, that with a higher quality rating there was 49, the same quality rating there was 32, a lower quality rating there was 52, and then the total number that I'm working with in my sample was 133. Okay. So, what percentages am I going to have? Well, if I look at my buyers, those that rated it higher quality was 20 out of the 36. So proportionally, 20 out of the 36, or about 55%, rated that as high. And so I could come over here and say, hey, you know what? All of that group rated it high. What about the non-buyers? Well, for the non-buyers, 29 out of the 97 rated the quality as high, so it does seem that there is a lower proportion of the non-buyers rating it as a high quality filter. Right? We complete the table as follows. So we could complete the table as follows, and I want you to look closely and always double check this, because if you look closely, right, 7 out of 36 is about 0.20, so about 20%. And 25 out of 97 is about 0.26, so about 26%. But notice that this in blue actually represents the center area, which is for rating the same. But down here, I have it listed as lower. Okay, so always check your labels so that we can come over here and we can say, oh my goodness, right? That lower shouldn't have been written as lower, right? But rather it should have been written as same. And that same should not have been written as same, but rather should have been written as lower, if we're going to have our graphs match up. So always be careful, always check. Okay, so we've made our well-labeled bar graph. We have our pieces here, right? We have up to a total of 100%. Okay, however, we are not done yet because it does also ask us to describe what you see. Alright, so what do we see? Okay, we notice that the segmented bar graphs are different, right? And that would seem to be an indication that we have an association between those that buy and their opinions and those that do not buy and their opinions towards these recycled paper coffee filters. Okay, so buyers seem to have a higher rate of higher quality opinion, about 55%, while non-buyers have a higher rate of the same or lower quality opinion, which is about 70%. Okay. So try and finish this out, right? The next steps are fairly straightforward, but unpause the video where you need and follow along. So what would be appropriate hypotheses that we're working for the chi-square test for independence in this setting? All right. We'll use alpha as 0.05 for our significance level. And the null hypothesis would be that there is no association between our variables and our categories. So no association between buyers and non-buyers and the opinion on the quality of recycled paper coffee filters, while the alternative would be that there is an association. Okay. What about the next part of the question? For the expected counts of a chi-square test for independence, assuming the null hypothesis is true, the formula that we can use is this formula. Right, that the expected value for a particular row, particular column, is given by that row total times the column total all over the total. So therefore, E11 represents row 1, column 1. Right, so if I come up here, row 1, column 1, so this position has a row total of 49, a column total of 36, a total of 133. So row, total, column, total, which ends up being about 13.3. If I want to look at row 1, column 2, row 1, column 2 is going to be this position, non-buyers that rate at higher quality. Okay. Well, what do I have? The row total, the column total, the total. So row total, column total, and that's about 35.7. And we can do that for the rest of these. Right? So as I said, we could do this for the rest of these, calculate each of those, not too hard, or we could let our calculator show this, right? But whenever it says compute, right, we need to show what formula we're going to use and show a couple of the calculations, and then we could use our technology to get the rest. So how do we do that? We come to our technology, turn it on. Okay, we need to make sure that we get our matrix in, and we're going to put that simply into matrix A. We have a 3-row, 2-column matrix. Okay, and 20, 29, 7, 25, 9, 43. Those are the values that we have from our matrix. Okay, then we can do our stat test, and we can do our chi-square test. Right, and our observed data is in this matrix, and the expected data, we can really and truly pick whatever matrix we want. So let's say I go to matrix F. That's fine. It just means that I'm going to store my information in matrix F. Right, so I'll go through and calculate, and I have these values. Now, these values for the chi-squared statistic I'm probably going to need later on, so I'm just going to go ahead and jot them down. That I have a chi-squared of 7.64. I have a p-value of 0.022, and I have degrees of freedom of 2. Right? I'm just going to go ahead and jot those down because I'll probably need them later. But what was I looking for right now? My expected counts. And my expected counts we put into matrix F, and look, it already made the matrix for us. Right? So we look to our matrix and we see, hey, let's check this out. Right? In my first row, first column, about 13.3. Yes. Right? Then first row, second column, about 35.7. Yes. So I just need to finish this out. Right? And doing it sequentially. Second row, first column, about 8.7. Second row, second column, about 23.3. Okay. Third row, first column, about 14.1. And third row, second column, about 37.9. So there are, right, excuse me, let me zoom back out. There we go. So there are my computed expected counts, assuming the null hypothesis is true. Right? And we have shown our work. Okay. Calculate the chi-square statistic, degrees of freedom, and the p-value. Well, these are the numbers, but guess what? When it says calculate, this is not good enough. I need to show what the setup is to get those numbers. Pause the video, think of what you might need to show, unpause to see if you've done it correctly. Okay, so let's check this out. What do I have? Well, what I have is for chi-squared, I need to show the formula I'm going to use, and let me substitute a few values into the formula. Where did these values come from? Well, how many did I observe in this first row, first column? 20. What was my expected value? 13.3. Observed minus expected, quantity squared, all over 13.3. And what about my last one? Observed, 43. Row 3, column 2. Right? So observed minus expected, quantity squared, all over. And if I add those all up, that's the 7.64. Okay. What about what I need to show for the p-value and for the degrees of freedom? Okay. Well, for the p-value, what does the p-value represent? It represents the probability that my chi-squared is at least 7.64. And really, I could put this or equal to down there. It's a continuous distribution, so it's not going to make a difference. Right? But my p-value is going to be the probability that my chi-squared is at least 7.64 with row minus 1 times column minus 1 degrees of freedom. How many rows? 3. Right? So what is this? This is 3 minus 1 times 2 minus 1. So that degrees of freedom is 2. And the calculated p-value is 0.022. Okay? So the last little piece is the conclusion that you would draw. Pause the video, think of your conclusion, then unpause the video and check. So what is our conclusion, right? Well, because the p-value is less than the significance level, right, 0.022 is less than 0.05, we reject the null. We have convincing evidence of an association between the purchase of recycled paper coffee filters and their perceived quality. Okay? You will get better at this by practicing. There is a lot of steps to remember. However, hopefully you're starting to see the similarities between the various steps for inference with the various tests. And as you're not sure about some things, look and ask questions for clarification so that you can improve.